So I don't have any model question paper for this course. So questions will be MCQ, fill in the blank, all those types. I don't think there will be any long form questions. It will be objective questions only mostly. I think professor has already answered this in the Google forum. The discussion forum, this question has been answered by the professor. Yeah, so I checked. So this is going to be an offline exam, and it will it will be a subjective. So it will have an MCQ, true, false, fill in the blanks, short answer type, as well as some long answers also. Long answers, I think, won't be much about derivation or essay. No, derivations can be there, like for Bragg's law and all, or and it will mostly be long numerical. Most of the long answer type will be long numerical questions. Like you are given some data and you have to extract values. So we can start. So welcome to the course Material Characterization by Professor S. Shankaran from IT with us. So this is the live problem solving session for week 10 of the course. I am Mayank Goyal. I am a research scholar in the Department of Electrical Engineering, IIT Bombay. The course is being taught by Professor S. Shankaran, who is a associate professor at the Department of Metallurgical and Materials Engineering, IIT Madras. The course plan for week 10 is to study tutorials and introduction to transmission electron microscopy. So this live tutorial session is happening every Sunday 6 p.m. to 8 p.m. at the Google Meet link. So first I will give an overview. so so let's revise what we studied in XRD. So first we studied the X-ray generation. So the wavelength of X-rays is given by the incident, the energy, acceleration energy, which uses the formula lambda equals to hc by e. And using this formula, we calculate the short wavelength limit, which is lambda SW is equal to 1.243 by V. So we studied this that if this the sine theta is proportional to lambda, so if your incident wavelength is higher, then the angular position of diffraction peaks will be higher also. So like the molybdenum, which has very low wavelength, short will have same peak occurring at a shorter shorter diffraction angle, whereas chromium which has higher wavelength will show the same peak at a higher angle. so the so the atomic scattering factor decreases exponentially with as uh, as a function of sine theta by lambda, and heavier elements have a heavier elements have more electrons, so they have higher initial scattering factor, but their decay function is also higher. So as the scattering angle, which is sine theta by lambda, increases, your scattering factor intensity decreases, which is why at higher angles you get lower intensity. So if you have a mixed lattice such as NaCl, your Miller index will be your structure factor will comprise from individual structure factors. So in this case, if HKL are all even, your final factor will be 4FNA plus 4FCl. If HKL are all odd, your final factor will be 4FNA minus FCl. So it won't. So since FNA and FCl are not the same, so it will be different. And if HKL are mixed, then F is equal to 0, because both Na and Cl form FCC lattices individually. So for mixed HKL, it will be 0. Uh, So how Bragg angle is calculated from deflection angle? So if the lat deflection angle is 18.4 degree, so Bragg angle would be 2 theta equals to 180 minus y. So Bragg angle would be 80.8 degrees. So this is a difference between deflection angle and Bragg angle. Then we studied the different selection rules for HK for BCC. H plus K plus L should be even. So allowed planes are 110, 200, 211, 220, 310. For FCC, HK have to be all even and all odd or all odd. So 111, 200, 220, 311, 222. These are the allowed planes. So how do you get final crystal structure from the peak values? So let's say you have peak initial 2 theta peaks at 20.3 degree, 29.2 degree, 36.7 degree, 43.6 degree. So from that, first you calculate your theta, which is half of 2 theta. From there, you get your sine squared theta. And from sine squared theta, you calculate the d spacing, which is n lambda by 2 sine m lambda by 2 sine theta. and and so you take the value of sine squared theta. So sine square, sine squared theta will be proportional to h square plus k square plus l square. Because d is proportional to 1 by square root of h square plus k square plus l square. So d square is proportional to 1 by h square plus k square plus l square. So sine square theta is proportional to h square plus k square l square. So you take the sine square theta values, you take their ratio and you convert them to integers. And from that you can get your h square plus k square plus l square values, which let's say here they come out to be 2468. So from there you can get your Miller indices. So from looking at your h square plus k square plus l square values, you can get the lattice structure. So here it will come out to be BCC, and that will give your Miller indice is 110, 200, 211, 220. So you take the raw data, you then use you calculate sine square theta values and you take the ratio. And from their ratio you get the lattice structure. Then you calculate Miller indices, and from there you can calculate your lattice parameter lambda under root h square plus k square plus l square by 2 sine theta. So that will give you your lattice parameter, and from there you know the lattice structure and the lattice parameter. From there you can calculate, you can compare it with the reference values and you can get which element is present. So here it's tungsten, because tungsten has a BCC structure and lattice parameter around 3.18 angstrom. Then when we studied peak broadening, where Schreier equation is B equals to K lambda by L cos theta. So from your peak broadening, you can calculate a crystallite size, strain, etc. using Williamson Hall plot. So all this, so I suggest you do some problems from this part, where you take some you take some XRD graphs, and from there you calculate the lattice parameter and the final element you figure out, because this type of question is most likely to come. It is very common XRD problem. Then we come to TEM, transmission electron microscopy. So TEM is it's a all the basics of TEM are the same as the basics of SEM, the electron microscope, because it's also electron microscopy. SEM is also electron microscopy, so the initial basics is the same. Just the difference comes data book, as in what data book are you talking about? So in the exam, if you are required to identify the element, then the parameter. So in the exam, if you are required to identify an element from the lattice parameter and crystal structure, then the reference values will be given to you in the question itself. So the type of questions I told, like it's going to an offline exam, so you will get some subjective type questions as well as objective type questions. So there will be MCQs, fill in the blanks, true false questions. Then there will be short answer questions as well as long answer questions. And long answer questions will mostly be derivations and long numerical questions where you are given some data and you have to extract values and parameters. Like for XRD, one of the most likely questions would be you are given some 2 theta values and you are asked to find the lattice parameter and the crystal structure, and you can also be given like maybe peak broadening pre FWHM values, and you may be asked to calculate the crystallite size and strain values. So those are very common XRD problems. So in TM, so the basics are same as SEM, so only the difference comes in detection. So again we come back to electron resolution. So electrons have a much lower wavelength than visible light. So visible light limit is around tens or to hundreds of nanometers, whereas electron beam has a resolution to in almost picometers. So if you have a 100 kilo electron volt electron, the wavelength drops to approximately 4 picometer, which is even smaller than a single atom. So you in TM you can even look at individual atoms. So TM is generally used to read the subatomic architecture. So they are not just photographs; they are maps of internal material integrity. So what's inside the material you can understand using TM. So so TM is generally used for things. One is imaging and one is diffraction. So imaging it you you visualize physical defects, metallurgical dislocations, and precise atomic location positions. So since the resolution is much greater than atoms, you can zoom into atomic level and see exactly where atoms are sitting with respect to each other. So so in XRD we are visual we are using spectroscopy to understand the lattice structure. In TM, you can see the lattice structure itself, where atoms are individually sitting. Then in diffraction, you can use the use diffraction to reveal precise crystal structure as well as lattice repeat distances and crystallographic symmetry. So you can use diffraction in TM to get the exact reciprocal lattice, which gives you the crystal structure at very high precision, as well as the and since it's very localized, so the beam size is very small, so it's highly localized. So you can look around and see how the lattice is changing across the sample. So you can see where the how much lattice is repeating and what is the symmetry inside the lattice. So one problem with TM is that it does not have depth sensitivity. So since the depth of focus is very high in in electron microscopy, so TM and the depths required for TM imaging. So TM means transmission. So the electron is the TM detectors are sitting beneath your sample. So it is detecting the electrons that are transmitted through your sample. So to get electron transmission, we have to have very thin samples. They are so thin that they're much smaller than the depth of focus of TM, and due to that there is no depth sensitivity in TM. So every image and every diffraction pattern or spectro in TM is averaged out across the whole depth, whole thickness of the specimen. And due to this, sometimes in bright field TM micrographs, there can be misleading. So from the microscope's internal electromagnetic radiation, we can get some spots on on our TM readings, which we can which we can think of as coming from our material. So you can see here in the two images. So first one is the damage caused from electromagnetic radiation, and second one is the actual reading from second phase particles. And you can see both of them look very similar. And since there is no depth of perception, we can't understand the difference between the two. So never rely on a single micrograph. True interpretation requires combination of crystallographic data as well, dark field imaging, as well as correlated bright field imaging. So not just a single bright field photograph should be used. So when an electron beam hits a thin crystalline sample, scattering changes both the spatial and angular distribution of the emerging electrons. So elastically scattered are coherent samples which occur at very low angles, 1 to 10 degrees, whereas inelastically scattered incoherent are occur at highly super low degrees, which are less than 1 degree. And due to that we don't take directly transmitted electrons. We take a slightly off angle. The detector is slightly off angle. So when a coherent beam is hitting a thin sample, so first there will be scattered electrons and backscattered electrons, which will come out from the top of the sample, which are what are used in SCM. Then there will be beam that will be going directly down path B. So that is not taken because it consists of inelastic electrons also. So instead we take a path C, which are transmitted at a slight angle, and that is used as a TM signal. So this slight angle is roughly 10 milliradians. I don't think previous year question papers are not available, as far as I know, for any NPTEL course. So infinite. So the lack of depth sensitive TM is coming because of its greater greater optics. So in generic optical lenses, the angles are very wide, and which results in a shorter depth of focus. But in TM, the conversion angles are extremely small, and because of that, there is not much divergence in the end, which results in a higher depth of focus. And combined with very thin samples results in zero depth sensitivity. So for a collection semi-angle of 10 milliradians and the required magnification of 50,000 x, if you want to observe a 2 angstrom detail, uh, the resulting calculation indicates that the depth of focus will be 5 kilometers. So you can see how large, almost infinite depth of focus is present in TM. So the Rayleigh criterion limit. So even without lens aberrations, finite lens sizes diffract electrons into blurry disks, airy disks. So instead of perfect points, there are slightly disks. So they result in Gaussian distribution. And the human's eyes can only resolve two distinct points. So the intensity profile between them dips at least 80% of the maximum. And that is given as Rayleigh criterion 0.61 into lambda by beta. And then you have aberrations. So spherical aberrations is virtually impossible to eliminate in electromagnetic lenses. So we must find optimal aperture angle where diffraction error and spherical aberration perfectly balance. So in one side you have diffraction error, and the other side you have spherical aberrations. So in the mid you add them up and you take the middle point, the lowest error point, which comes out to be R total equals to RTH square plus R spherical square into half, power of half. So beta optimum comes out to be 0.77 lambda by CS 1 by 4. So for 100 kilovolt electron practical resolution rests at 0.15 to zero point 0.3 nanometers. So even though the wavelength is very small, like in picometers, the practical resolution is still in angstroms, almost the size of atom. So TM hardware is a direct analog of a light microscope built entirely of electromagnetic lenses. And since all lenses are imperfect, they have to filter out scattered radiation. So perfect image is physically impossible. So again, you have a electron gun to generate your electrons. Then you have condenser lenses to focus the light on your sample. Then you have objective lens to collect the light, transmitted light, which then goes to your projector lenses and then your detector. So again, as there are two types of electron sources, thermionic sources and field emission sources. So thermionic sources are driven by heat and produce a less monochromatic spread electron distributions, whereas field emission sources are driven by extraction voltage and they produce highly monochromatic electrons which focus at a remarkably fine crossover point. So that gives us very good very good images, very high resolution. So the here, as we studied in SCM, we use electromagnetic lenses instead of glass lenses for optical. So you have copper coils which act as an electromagnet, and you have water inlets and outlets for cooling down your coils. And then you have a center bore center hollow where your electron passes through. So the magnetic field is weakest on the optical axis. Its strength increases sharply towards the pole pieces, acting as an invisible funnel that forces off-axis electrons back towards the center. So the magnetic field is spread, not constant throughout the gap. It is weak in the middle and strong out at the out near the near the piece electromagnet pieces. So the electrons going away from the center are pushed back towards the center, and focus is controlled by the bore to gap ratio and the current running through the coils. So the TM ecosystem first contains hardware and constraints. So you have your sample holders, you have pumps to create vacuum, then you have contamination control to prevent any contamination. Then there's beam generation and control. So the what what voltage selection, apertures, you want parallel beams or convergent beams. Then beam manipulation, so alignment, astigmatism, focusing, and then you have signal detection where if you want the flipped images, you want bright field imaging, dark field imaging, you want to do STM, which is scanning tunneling electron microscope, or you want to see diffraction. So you have apertures, you use apertures to control some parameters. So they are made from platinum and molybdenum, and their um, thickness is in microns with perforations in micron ranges. So they control your collection angle beta, your image resolution which is formed by the lens, your depth of field, depth of focus, your image contrast, and the angular resolution of the diffraction pattern. Then you have contamination control. So you can have hydrocarbon contamination. What will happen is residual hydrocarbons from pump oil crack under the electron beam. So if you have carbonaceous material deposits on a specimen, they and you have hydrocarbons present, so they will crack under the electron beam and they will obscure the high resolution image analysis. So countermeasures are used. So we heat the samples above 100 C so to evaporate any contaminations, or we cool the specimen to liquid nitrogen temperatures to avoid water vapor to condense as surface ice. No, so heating avoids water, but if we are cooling, we will have the issue. If there's water vapor present, it will condense on the surface as ice. Earlier detection was done on photographic fluorescent screens and films. Now we use digital recording systems to reduce reliance on photographic films, and we don't have to keep changing the film. So the system remains closed, and it improves overall TM vacuum quality. So you have different type of TM holders. One is single tilt holder, so it rotates on a single axis. This is the standard choice for normal conventional imaging. Then you can also have double tilt holder, which can tilt at two orthogonal axes. It is essential if you want to do precise defect analysis or any analytical work, and it obtains and to obtain specific contrast mechanisms. Then you have heating cooling holder, which can heat or cool your sample, so it can enable localized thermal control, and it is crucial to if you want to observe in situ phase transformations and thermal responses. Then you can have rotation holder, which allows in plane specimen rotation, which is optimized for analyzing orientation effects and crystallographic symmetry operations. So normally holders can accommodate specimens around 3 millimeters size, and you can also have multi sample holders, which allow multiple specimens to be loaded simultaneously into the vacuum. So you don't have to keep changing the sample every time by breaking the vacuum. So there's a trade-off. So you can't just operate at so you can't just always operate at the maximum kV to get maximum performance. So some materials cannot operate at high kVs. Like there are beam sensitive materials like polymers, biological samples, and some ceramics. So they have to use low kilovolts, low kV acceleration voltage to minimize the devastating radiation beam damage. But Otherwise, you operate at the maximum available voltage, which which for most TMs should be around 100 kilovolts or 200 kilovolts. Some can even go up. Nowadays, you can even get up 300 kilovolt and above TMs also. So they are generally used for metals where the damage threshold is greater than typically 400 kilovolts. So benefits are you get better gun brightness, shorter wavelengths, which gets you better resolution using de Broglie relation, smaller inelastic scattering cross section, so you have more elastic scattering area, and it also reduces localized heating effect. So typically we use fluorescent screen, which uses cathodoluminescence to convert electrons to visible light. So what happens is that on your so this is your detector fluorescent screen. So it has a long delay phosphor coated fluorescent screen. So when the electron beam focus that coming from your sample hits this, it emits light. So the display screen emits light in exact proportion to the intensity of electrons falling on it. So it provides a interface between the electron beam and the human eye. So then you can have parallel beam or convergent beam. So and for parallel beam, a smaller second aperture creates a more parallel beam. It is essential for conventional second selected area diffraction (SAD) because it ensures that diffracted spots are focused to their sharpest possible points. So SAD is a technique used in TM to see the electron diffraction or reciprocal space, and it is done at a very specific selected area. So it's called SAD, selected area diffraction, and for that you use parallel beam so that you get sharpest possible points. So and for convergent beam, so you need a strong C1 crossover to create smaller probe and a weak crossover to create a large probe, and it requires a large UV lens ratio, U by V ratio. So it is used for localized signal for minute specimen areas. So it is used for microanalysis, STM, and micro nano diffraction. So if you want to see very minute areas like in nanometers or less, there you would use convergent beams. So then we do beam alignment and astigmatism. So if there can be misaligned beams, so we have a high precision reticle where you align your beam. So if the image of the beam, if C2 lens is under focused or over focused, the beam image of the beam will sweep off axis. So we have to bring it back. then then you can have perfectly aligned beam. So the beam here the beam will remain perfectly circular, and it will symmetrically expand and contract about the optical axis during under focusing and over focusing. Then you can have astigmatism where as the C2 lens is under focused or over focused, the the beam gets distorted elliptically, and this oval shaped flips between horizontal and vertical as it gets over focused and under focused. That is the example that you have astigmatism. So you can use the videos uploaded by by me or the other TA to create notes. So then lens flip. So if you want to do imaging or if you want to do refraction, you change the lens accordingly. So in imaging mode, so I don't have any handwritten notes. So in imaging mode, the lens action would be, so the intermediate lens is adjusted, so its object plane is the image plane of the objective lens, and the objective aperture is inside, that is on optical axis, and the SAD aperture is outside, and the result is that a spatial image is projected on the viewing screen. And in diffraction mode, the intermediate lens is adjusted, so its optical plane is on the back focal plane of the objective lens, so instead of the image plane, and the objective aperture is taken out and the SAD aperture is inserted. So you can see here, objective aperture is inside here and the SAD aperture is inside here. So instead of getting the spatial image, the result, you get a diffraction dot pattern on the viewing screen. So I don't have any model question paper for this course. You might ask the professor in the discussion forum. Next is contrast control. So bright field versus dark field imaging. So in bright field imaging, your object, the aperture is towards the center, so it's centered directly on the optical axis. Whereas in dark field imaging, the aperture is centered at a specific diffracted spot using a beam tilt operation. So in bright field, the selected beam selected, that is, it allows only the zero ordered transmitted beam to pass, whereas in diffracted it allows one specific diffracted beam to pass. So in bright field imaging, the result is that the dense areas scatter electron and appear dark, whereas thin areas transmit and appear bright. Whereas in dark field imaging, since only one specific diffracted beam is passing, it highlights only the specific crystallite planes contributing to that exact diffracted beam. So instead of intensity, here we are looking at crystallite planes of particular beam. So then STM, which is similar to SCM. because it also involves scanning, but here the detectors are looking at the transmitted electrons instead of backscatter electrons or secondary electrons. So hence it's STM, scanning transmitted electron microscopy. So it also uses scan coils. So two pairs of scan coils located below the C2 lens and other upper objective pole piece sweeps a convergent electron probe parallel to the optoelectrons across an electron transparent specimen. So there are scan coils which deflect the beam, so it can be scanned across your specimen. so it so it features an annular dark field detector, which so it's a physical ring which blocks the transmitted central intensity on only strictly collects the scattered dark field intensity. So the application is to produce a highly localized signal fundamentally optimized for chemical analysis and electoral elemental mapping across specific material features. Next is TM diffraction. So it can be used to extract crystallography. So first you can see if the specimen is crystalline. So that is evaluated by presence of shard geometric draw versus diffuse ring. So if the specimen is not crystalline, you will get rings instead of very fine spots. If you are getting very sharp spots, then it means the sample is crystalline. Next, you can see if the sample is monocrystalline. So monocrystallinity is confirmed by a single uniform grid of diffracted spots. So if it's polycrystalline, there will be multiple grids of diffracted spots, whereas for monocrystalline only one grid will be there. Then you can calculate the orientation relate. So it is calculated related to the incident electron beam passing through the specimen. You can get the orientation of your specimen. You can get your grain morphology and size. So it is determined by analyzing the patterns, scale, and extreme sharpness of individual spots. And you can also see if multiple phases are present. So it is indicated by overlapping or distinct secondary grids within the primary pattern. So different phase will have grid different phase will have different grid types, grids which can overlap each other if the multiple phases are present. That we can figure that out. So diffraction has to be calibrated by the formula RD equals to lambda L. So where D is the lattice spacing of the crystal, R is the distance of transmitted central beam to the diffracted spot on screen, and L, which is this camera length, that is distance from specimen to screen. So lambda L is a camera constant. So lambda is a calibrated camera constant. It must be mathematically calibrated against a non-standard sample before any serious indexing or crystallographic analysis can occur. So first you bring in a standard sample for which you already know the crystallographic parameters. You take its diffraction pattern and you use that to calibrate your lambda L value. And after that only you can bring in an unknown sample for analysis. The TM analytical triad. So it can generally be used for three different parameters. Spatial, first is conventional imaging, which is used for spatial structure. Second is STM, which is used for chemical structure. And third is diffraction, which is used for crystallographic structure. So conventional imaging uses parallel beam plus image plane focus. It uses bright field and dark field imaging. So it answers where are the features, defects, and boundaries. Then in STM, use conversion scanning probe and annular dark field detector. The output is Z contrast imaging or elemental mapping. So it answers which what elements makes up those features. Then you have diffraction crystallographic structure. It uses parallel or convergent beam plus back focal plane focus. So it output SAD or nano diffraction spot patterns, and it answers how are the atoms fundamentally arranged. So now I will show you some questions regarding this week's. The depth of focus in electron microscopy is very high. True or false? You can write your answer in the chat. That is correct. So we just studied that depth of focus is very high in electron microscopy compared to optical microscopy. Condenser lens controls the size and intensity of electron beam in TM. True or false? That is it. It is true. So the the strength of the condenser lens determines the size and intensity of the electron beam combined with the condenser aperture.
Condenser lens controls the size and intensity of electrons. Size
What?
condenser lens controls the size and intensity of electrons. Size
Uh,
and
I am not able to understand you. Why TM why TM images have much higher resolution than images from light microscope? Am I audible now? So the correct answer would be B. So, so electrons so we can generate electrons at much shorter wavelength than visible light. In like visible light has wavelengths of around few hundred nanometers, whereas we can generate electrons having wavelength in picometers. And using Rayleigh criterion, this results in much higher resolution. Dash is observed if the sample is bent in a TM bright field image. Fringes and grain boundaries, Kikuchi pattern, contours. So the answer will be C, contour. So if the sample is bent, the light diffraction will transmission of light will be slightly off axis, which will result in contours. What is the wavelength of electron beam accelerated by a voltage of 200 kilo electron volts without considering relativistic effect? 0.0005 nanometers, 0.0027 nanometers, 0.05 nanometers, 0.0095 nanometers. So the answer here to be 0.0027 nanometers. So we use the de Broglie equation to calculate the wavelength of electron, which is 1.22 by square root E. And this gives us the for the solution 0.0027 nanometers, that is 2.7 picometers. What is the theoretical resolution according to Rayleigh criterion of the electron lens illuminated with the wavelength of 0.0037 nanometer and semi-aperture angle of 5 milliradian? 0.4514 nanometers, 1.52 nanometers, 0.0343 nanometers, 0.0039 nanometers. So the answer to be A. So the Rayleigh criterion formula is 0.61 lambda by sine alpha. So putting uh, lambda is 0.0037 and alpha is 5 milliradian, which is 0.005. We get the result as 0.4514 nanometers. What is the resolution of the above lens having a CS of 3 millimeters, that is spherical aberration constant of 3 millimeters, 0.000212 nanometers, 0.00464 nanometers, 0.000029 nanometers, 0.0129 nanometers. So, so you have to use the values from the previous question as well as this question, which is CS equals to 3 mm, which is a constant of spherical aberration. So the answer to be A. So you have to use the formula optim R equals to 0.61 lambda. So you have to use the optimum value, which is 0.61 lambda beta plus cs into beta cube square half. So how is the depth of field and depth of focus affected by using small apertures? Depth of field increases and depth of focus decreases. Depth of field decreases and depth of focus increases. Both depth of field and depth of focus increases. Both depth of field and depth of focus decrease. So the answer is C. So both will increase. So we are by using small aperture, we are reducing collection angle. So both will increase. The formula for depth of field is d objective by beta objective m square, and depth of d objective by beta objective. So both of them will increase. So this thing we had already studied in SCM. What is the range of elastic scattering angle while forward scattering in TM? 1 to 10 degrees, 10 to 20 degrees, 15 to 25 degrees, or 20 to 30 degrees. So the answer to this is A, 1 to 10 degrees. With this we studied just now. So For elastic scattering, the range is 1 to 10 degrees, and for inelastic scattering, the range is less than 1 degrees. So hence we keep the detector slightly off axis at around 10 milliradians. Which of the following statements is true? Dark field image is formed by blocking the diffracted beam and allowing only the transmitted beam to pass through. Blocking the transmitted beam and allowing the diffracted beam to pass through. Tilted the incident beam such that diffracted beam pass through the center and blocking the transmitted beam. Tilted the incident beam such that diffracted beam is blocked and only direct beam is allowed to pass through. So the answer would be B and C. So dark field image is formed by tilting the incident beam to block the transmitted beam and allow the diffracted beam to pass through, which is the same point conveyed in B. The first three reflections of a disordered FCC crystal are 111, 200, 220, 110, 110, 220, 220, 220, 220. So the answer is A, 1. So for FCG crystal, the H scale values should be all even or odd, which is only satisfied by option A here. So calculate the structure factor for Ni3Al, the crystal section is shown in the below schematic. So FHKL equals to FAL plus FNI minus 1 per H plus K plus minus 1 per H plus L plus minus 1 per K plus L. FHKL equals to FAL plus 3NI for all values of HKL. FHKL equals to 4 FAL plus FNI for unmixed indices. FHKL equals to FNI plus FAL minus 1 per H plus K plus minus 1 per H plus L plus minus 1 per K plus L. So the correct answer here is A. So as you can see here, the aluminium is sitting is occupying only the corner position. So the coordinate for aluminium will be 0, 0, 0, and nickel is occupying only the face centered positions. So the coordinates for nickel will be half of 0, half 0, half, and 0, half, half. And so for 0, 0, 0, the it will become e power 0, 0, 0. So it will only come out as FAL, and for FNI it will become minus 1 per, for half of 0 it will become minus 1 per H plus K, for half zero half it will be minus 1 per h plus l, and for zero half half it will be minus 1 per k plus l. So the final answer will be FAL plus FNI into this, which is A part. So that is everything I had for today. Thank you for attending the session. If you have any questions, you can ask, or if you want, you can leave the chat. So to calculate the structure factor, we use the formula. So FAL is the scattering factor for aluminium, and FNI is the scattering factor for nickel. To calculate the structure factor, we use the formula. F equals to F e per iota theta, which is your scattering angle, and scattering angle can be written in terms of HKL. So, and so if you have a cubic lattice, so any point on a cubic lattice is equivalent. Any point at the corner of a cubic lattice is equivalent. So we only take just one point of the cubic lattice, which is your 0, 0, 0 point. So if you put that 0, 0, 0 point here, this term becomes 1. So you are only left with F scattering factor. So here the 0, 0 point is only occupied by aluminium. So we only get FAL. And if you see each of these, so the face centered points are formed by three different cubic lattices. Each the coordinates of each one would be half 0, half 0 half, and 0 half half. And if you put half 0 here, so for half it will this will become minus 1. So it will become minus 1 par h. And since k is also it's half 0, so for k also it will become minus 1 par k. So it will become minus 1 par h plus k. Similarly, for half 0 half, it will become minus 1 per h plus l. And for half 0 half half, it will become minus 1 per k plus l. So then you can combine them as minus. So since these are only nickel atoms, so it will be multiplied by nickel scattering factor. So this will be the final answer. If instead of it was a single If it was single element, everything was nickel, then this FAL would also have been FNI, and then you could have taken FNI common. It would come 1 plus minus 1 H plus K minus 1 H plus L minus 1 K plus L. That is the formula for your normal FCC lattice, and then you could have used the formula that FHKL would be FNI if HKL are all even or all odd. So this is a type of short answer question that can come, and I already suggested long answer type questions from XRD can be like to derive Bragg's law, or you can have some XRD data values where you have the peak positions and the intensity and the FWHM values, and you might be asked to calculate the lattice parameter and the crystal structure, and you can also be asked to calculate the strain value and the crystallite size using the Williamson Hall plot.